Hello, welcome to my presentation of my dissertation. I am Tananon Jewapatharakun, a Master Computer Science student under the supervision of Dr. Supao Singh Gill. The topic of my research is MambaNet0, a Mamba-based sustainable cloud resource prediction framework towards net zero goals. In today's landscape, cloud computing has cemented itself as an integral component in today's digital landscape. The paradigm has seen global adoption and plays a massive role in the advancement of multiple fields like Internet of Things, artificial intelligence, and big data. The growth of cloud computing, however, brought new challenges that threatens long-term sustainability goals. For cloud services and applications to function, they are provisioned computational resources from data centers. However, due to the volatile nature of the demands for these cloud services, it is difficult to estimate the exact resources required at any given point, creating inefficiencies within the allocation process. Thus, this leads us back to the problem statement, which is our inability to accurately predict the demand for cloud resources, leading to an over reliance on over provisioning. In order for these cloud applications to maintain quality of service, they often over provision resources to the applications, mitigating the risk that they will lack the computational resources needed to stay functional. To the right, you can see a figure which represents the CPU utilization on a cloud environment consisting of thousands of virtual machines. This graph was from the dataset utilized to train the model, which will be explained a bit later. Here's a closer look at the graph. The yellow represents the provisioned CPU capacity, while the blue represents the actual utilized CPU capacity. The gap between the two lines represents the inefficiencies of the cloud resource allocation. As you can see, not only that the gap between them are massive, the graph indicates that the cloud resources are also almost always over-provisioned. On average, the provisioned CPU capacity exceeds the actual CPU usage by 9 times. This massive inefficiency is the key motivation to this research. With countries like the UK striving towards net zero objectives, these unutilized resources could be a significant step towards achieving sustainable goals like reduced carbon emissions. With the growth of AI contributing in enormous energy consumption alongside cloud computing, its predictive capabilities shows promise. There have been multiple studies that aim to predict CPU utilization from cloud environment as seen on the table. The first three study on the table utilizes traditional time series forecasting like ARIMA, LSTM, and RNN models to provide highly accurate results. However, these studies assume the stationarity of the time series data, which could limit their model's performance in real-world scenarios. Studies from Velu et al. And Wang et al. Addresses these issues by utilizing pre-trained deep learning models like Chronos and Deep AR, with the ability to better recognize trends and seasonality within the data. This research, as seen at the bottom of the table, seeks to further improve forecasting accuracy by introducing MambaNet0, a cloud resource prediction framework that leverages a novel deep learning model called Mamba. Mamba is a state space model developed to handle long sequential data efficiently. While the model was developed for language modeling, this research intends to explore its capabilities in predicting time series data, which is long and sequential by nature. BitBrain's Grid Workload Archive, or GWA T12 dataset, was utilized for training and evaluating the model's performance at time series forecasting on CPU usage. This figure illustrates the framework in detail, outlining its architecture and workflow of the framework in a real world scenario. The process begins with users interacting with cloud operations, which is handled by the cloud controller, receiving the requests and issuing commands to the virtual machines, while also provisioning them the computational resources required. The virtual machines, in turn, provides the services and the CPU utilization metrics back to the controller. The workload traces would then be stored on a Google Cloud storage. where it will be retrieved by the CPU usage forecaster implemented on Google Cloud's Vertex AI. There, a data processor cleans the data before sending it to the neural network. Here we can see a closer look into the CPU usage forecaster in Vertex AI, where the processed data is sent to the model through the input layer. The input layer then propagates the data forward into the Mamba blocks. The data then propagates forward further through n amounts of blocks, depending on the configuration. Then the results is sent through the output layer where the predictions are obtained. These predictions are sent back to the cloud controller so that it can provide accurate estimation of the required CPU capacity. In order to evaluate the performance of the Mamba model, three baseline models were chosen for comparison. The first is the autoregressive integrated moving average ARIMA. The model is widely used in time series forecasting due to its proven capabilities, thus making it a great choice as a baseline. Second is long short term memory, LSTM, a type of recurring neural network, RNN, that specializes in long sequential data similar to Mamba as it shares similar features of being able to maintain information. Third is Chronos, a set of pre-trained time series forecasting models that utilizes transformer-based architecture and tokenizes time series inputs similar to large language models. As Mamba's design was to address the limitations of transformer-based models, Chronos serves as a great baseline for comparison when performing on long sequential data. The error metrics used consist of mean absolute error, MAE, root mean squared error, RMSE, and symmetric mean absolute percentage error, SMAPE. The results of the experiment can be seen on the table to the left, with the Mamba model getting an MAE of 3.932, RMSE of 4.758, and SMAPE of 4.477. Both Chronos and Mamba was able to perform significantly better than the two traditional models, ARIMA and LSTM. However, Mamba did outperform Chronos as well, but at a smaller margin, being able to produce 2% less SMAPE. These results reinforce its effectiveness at providing accurate results and consistent predictions, demonstrating its potential in precise, proactive resource allocation. This figure illustrates the predicted CPU usage from Mamba compared to the actual CPU usage of the test set. This illustration highlights the accuracy of the model with its prediction not being too far off the actual CPU usage on the graph. Through its utilization of Mamba model to predict future resource usage, MambaNet0 enables proactive resource allocation for cloud servers to help mitigate inefficient resource provisioning. The framework was implemented and evaluated on Google Cloud's Vertex AI environment, where it outperforms established baseline models like ARIMA, LSTM, and Chronos by achieving 29% improvement in SMAPE against the top baseline model. These results underscore the potential of the Mamba model in providing accurate predictions for cloud resource utilization, which would lead to a reduction in operational costs along with supporting environmental and net zero goals. Next is a discussion of possible future directions. A deeper dive into the environmental impact that the framework would be an interesting prospect, especially towards net zero goals. The quantification of the reduction in energy consumption or carbon emissions could reveal the tangible benefits of accurate forecasting for cloud sustainability goals. Technologies like digital twin could be used to model daily energy consumption based on the forecasts made compared to the originally planned allocation. The generalization of the model could also be a possible avenue for future exploration. Despite its results, the model's ability to forecast CPU utilization was evaluated only through the BitBrains dataset. Exploring the model's performance on diverse datasets with different characteristics could further cement the model's robustness and adaptability to real-world cloud data. Another possible direction for future research would be to address the computational efficiency of the model. The Mamba model was designed to efficiently handle lengthy sequences, meaning that its performance on specialized hardware like GPUs should not be overlooked. With faster computational speed, overhead can be reduced both from both the training and predicting process. A reduction in computational overhead would enable the model to shorten the prediction intervals and provide better accuracy for dynamic cloud environments. Thank you for listening to my presentation.